Hello and welcome to lesson 8A. So here we are going to get started with chapter 2, and we are going to take a first look at the derivative today. So there is a handout that goes with today's lesson. It should be available to you in class notebook. If you haven't done so already and you want to go ahead and print this worksheet out, you can pause the video here if you're watching by yourself to go and print it. Otherwise, we are going to go ahead and get started. Today, we are introduced to the concept with which we will spend our greatest amount of time investigating in calculus, the derivative. So we're going to start by drawing a picture together. So we're going to use this picture for a pretty good portion of this handout. Let's start by drawing an axis. Now, on our axis, we need some function, f of x. Now we want to add a couple of points onto our function, so I'm going to start just with any point. And then since I don't really know much about this, I'm going to label my x value here as x. And then I want to actually label the point with that xy coordinate. So I know that my x term is just x, and then my y term is whatever I would get out of my function if I plugged in that x, so we can call that f of x. I want to actually add a second point, so I'm going to add another point on my function. Now, I don't know what this x value is, but I can write it in relation to my original x value. So since I have this first x value already labeled, I can label the distance between these two x values as h, which would make my new x value my original x value plus that distance of h, or x plus h. So to label that xy coordinate, I would label it with the x value, which is x plus h, and then my y value, which remember is what we get out of the function if you plug in an x plus h, so I can call that f of x plus h. So make sure you have this picture as we're going to be using it as we continue down this handout. So using that picture that we just created, we first want to identify what does the expression f of x plus h minus f of x over x plus h minus x represent in terms of the graph that we created. So let's first start looking at where we even see those values. So we see f of x plus h as a y value and f of x as a y value. So if we're finding the difference there, what we're really finding is the change in our y values. And then looking at the denominator, x plus h minus x, what we're looking at there is the difference in our x values. So we have the change in y over the change in our x values. And hopefully you recognize that the change in y over the change in x is something we've been talking about for years, and that is just the slope. But the slope of what? So here we have a curved function, so we know that we don't have a constant slope on f of x. But what we can do is we can actually draw a line that goes through those 2 points. So if you have a ruler, maybe grab one, or like a straight edge. I'm going to try my hardest to draw a straight line here, but no guarantees. So you want to be a straight line that goes through both of those points. Okay, not the best, but you get the idea. That's a straight line. And remember, a line that goes through a function at exactly 2 points is called our secant line. So that f of x plus h minus f of x over x plus h minus x is the slope of our secant line, which we have here in purple. And now this next question says, what does this expression f of x plus h minus f of x over x plus h minus x simplify to? So if we were to actually simplify that denominator, notice how we have x plus h minus x. That positive x and negative x are going to go away. So we're left with f of x plus h minus f of x over h, and hopefully you recognize that as something we've been using a ton already this year, and that is our difference quotient. So the next piece we want to look at says as h, which remember is the distance, between those two x values, x and x plus h. So as h approaches 0, what happens to the secant line? So that means as that distance is getting smaller, that means that those 2 points are actually getting closer and closer together on our graph. And as it's getting closer and closer to 0, it's hopefully approaching a single point, which means our secant line that was going through 2 points now becomes a tangent line, which is only going to go through the 1 point. And again, I'm going to try really hard to draw a straight line here that's only going to touch the function at that 1 point, but bear with me. So as h gets closer and closer to 0, the secant line, which was touching 2 points, becomes a tangent line, which remember is only going to touch the function at 1 point. All right, so we are going to put all of that all together, and we want to determine what does the limit as h approaches 0 of f of x plus h minus f of x over h represent. So remember, this f of x plus h minus f of x over h was the simplified version of the slope of the secant line. And then the limit as h goes to 0, means we're looking at what happens as that distance between our two x values is approaching 0. So the limit as h goes to 0 of f of x plus h minus f of x over h actually represents the slope of a tangent line, since that h value is getting closer and closer to 0, that is parallel, meaning it has the same slope, to the secant line. Which is pictured here. So let's suppose that our function f of x is negative x squared minus 4x plus 1, and we want to find the limit as h goes to 0 of f of x plus h minus f of x over h, so that quantity from before that we said represents the slope of that secant line. So to start, we're going to plug in our x plus h and using our function f of x. So we have negative x plus h squared minus 4 times x plus h plus 1, minus subtracting our whole function, so in parentheses, negative x squared minus 4x plus 1, and this is all over h. To start simplifying, let's start by squaring that first term, so negative on the outside. X plus h squared becomes x squared plus 2xh plus h squared. Then let's distribute our negative 4, so we get minus 4x minus 4h plus 1, and distributing our negative, we get plus x squared plus 4x minus 1, again, all over h. From here, I'm going to distribute my negative through that first term, so this becomes negative x squared minus 2xh minus h squared minus 4x minus 4h plus 1 plus x squared plus 4x minus 1, and that's all over h. And again, just go slowly through this to make sure that you are distributing negatives wherever appropriate. From here, hopefully we notice some things start to cancel. So we have negative x squared and x squared. We have negative 4x and positive 4x. We have a positive 1 and a negative 1. So this simplifies down to be negative 2xh minus h squared minus 4h all over h. Factoring an h out of the numerator, we get h times negative 2x minus h minus 4 all over h. These h's are going to cancel. So now we can just take the limit as h goes to 0 of our simplified function, so of negative 2x minus h minus 4. Direct substitution, now plugging a 0 in for h, gives us negative 2x minus 0 minus 4, which gives us negative 2x minus 4. So your result to this limit is defined to be the derivative f prime of x of the function f of x. So now we're going to take a look at what this derivative represents in terms of the graph of f. So our result for the limit as h goes to 0 of f of x plus h minus f of x over h for that function that we were given, negative x squared minus 4x plus 1, turned out to be a function in terms of x. So here we have pictured the graph of our original function f of x, and we just want to fill in this table to the left for the indicated x values and f prime of x, so our the function that we found. So we're first going to look at f prime of negative 4. So this was our result in our last slide. F prime of x was negative 2x minus 4. So we're going to start just by evaluating this at negative 4. So we would get negative 2 times negative 4 minus 4. Negative 2 times negative 4 gives us a positive 8 minus 4. So f prime of negative 4 equals 4. We're going to do the same thing for x equals negative 2 and x equals negative 1. So here we have f prime of negative 2, again just plugging into the function that we found on the last slide. Negative 2 times negative 2 minus 4 gives us 4 minus 4. So f prime of negative 2 just gives us 0. Finally, we want to find f prime of negative 1, again just plugging into that function. Negative 2 times negative 1 minus 4 gives us 2 minus 4. So we find f prime of negative 1 equals negative 2. So now that we plugged in those x values and we evaluated at f prime, we actually want to grab a ruler and investigate the graph that we have here. So we want to draw a tangent line. Remember, a tangent line is going to intersect with our function only one time at our given x value. And then we want to see what happens and how that's related to the function that we found. So we first want to find our tangent line at x equals negative 4. So we're going to go to x equals negative 4, and we're going to intersect just one time with a straight line. If you have a ruler, now would be a really awesome time to use it. Same thing, we're going to draw our tangent line at x equals negative 2. So at negative 2, we're going to draw a line that's going to intersect only one time. And then at negative 1, we're going to draw a line that intersects with our function only one time. So now that we have those three graphed, we want to investigate our graph, and we want to think, what does it appear that the derivative function f prime of x equals negative 2x minus 4, which remember is what we plugged into in this chart to get out those values, represents in terms of the graph at each given value of x. So let's start by looking at, f prime of negative 4, and what we got out was a positive 4. Looking at the tangent line that we graphed, we noticed that that tangent line has a slope of positive 4, right? It's a positive slope, pretty steep. We could count our slope if we wanted. Looking at x equals negative 2, that's right, slope. Looking at x equals negative 2, the tangent line there is actually a horizontal line, which remember has a slope of 0, which is also the value that we got out when we plugged negative 2 into that derivative function. Finally, looking at when x equals negative 1, excuse this typo, when x equals negative 1, the value we got out was negative 2. Looking at our tangent line, our slope is negative, not as steep as the first one, so here our slope is about negative 2, again matching with the value we got out of our derivative function. So in summary, we can say that f prime of x is an equation that can be evaluated to determine the slope of any tangent line drawn to the graph of f of x, at any value of x. So we can say f prime of x, our derivative function, is an equation that can be evaluated to determine the slope of any tangent line drawn to the graph of f of x at any value of x. Okay, so we just want to formalize everything that we sort of just looked at and went over. So we want to start with the definition of the derivative. So f prime of x, our derivative, is defined as the limit as h goes to 0 of f of x plus h minus f of x all over h. And what that represents, remember, f prime of a represents the slope of the tangent line drawn to the graph of f of x, specifically at x equals a. So we want to find the equation of the tangent line to f of x at each of the points below. Notice that we want to find a whole equation and not just the slope. So for the first one, we want to find the equation of the tangent line at x equals -4. So remember from our graph and what we found earlier, the slope of the tangent line at x equals -4 is 4. But then we also want to look at that intersection point. So we have the point where the tangent line intersects the function at -4, 1. So from here we want to use our y equals mx plus b and actually plug in for x, y, and m. So I'm going to plug in our 1 for y equals 4 times -4 plus b. So I get 1 equals -16 plus b. So adding 16, I get 17 equals b. So the equation of the tangent line, that blue line that we drew in earlier, is actually y equals 4x plus 17. So if we continued that blue line on, we would get 4x plus 17 as the equation. For the next one, the equation of the tangent line at x equals -2. Again, earlier we found that our slope was 0. But again, we want to find that entire equation, so we need to look at the point of tangency, which is here at -2, 5. Again, using y equals mx plus b, I'm going to plug in my x, y, and my m, so I have 5 equals 0 times -2 plus b, which gives me the equation y equals, which gives me 5 equals b, which gives me the equation y equals, plugging in my m, 0x plus 5, which leaves me with the equation y equals 5. And that is the equation of the tangent line. Looking at our red line that we drew in earlier, y equals 5 makes sense. Finally, I want to write the equation of the tangent line at x equals -1. From the work we did earlier, plugging -1 into that f prime derivative, we get that the slope is -2. And our point of tangency on the graph we can see is at -1, 4. Again, using y equals mx plus b, because we want the whole equation of the tangent line, we're going to plug in our x, y, and our m. So we're plugging in 4 equals -1, -2 for our slope times -1 for x plus b, which gives us 4 equals 2 plus b. Subtracting 2, we get 2 equals b. So the equation of that purple tangent line that we drew earlier is y equals, plugging in our slope of -2, x plus 2. Great job with these introduction activity. These concepts are going to be formalized and practiced in lesson 8b.